So today we will read about matrix iteration method and orthogonality principle. This matrix iteration method is suitable uh, to find basically the lowest eigen values, or you can say the natural frequencies and eigenvectors. Eigenvectors also known as mode shapes. Okay. For a multi degree of freedom system basically. Okay. The equation of motion, if you say the equation of motion uh, in terms of flexibility matrix can be expressed as A, that is the flexibility matrix, M जो है हमारा ये मास मैट्रिक्स है, and multiply by the acceleration plus x matrix is equal to 0. मान लो ये हमारा इक्वेशन 1 हो गया. Now we will use a solution x is equal to capital X sin omega t, then we will have its velocity will be the differentiation of this displacement. So it will be omega x cos omega t, and इसका जो acceleration है x double dot, that will be the differentiation of x dot, right. So it will be minus omega square x sin omega t, right. Now ये जो solution है, इस solution को हम इस will implement in this first equation 1 में हम substitute करेंगे. Now we can write substituting the value of x and x double dot, okay, in equation 1 we have minus omega square into x into matrix A into matrix M plus x is equal to 0, okay. Or we can say that its x is equal to omega square A into M into capital X, okay. So if we further simplify, we will take this multiplication of A and M as a new matrix, let that be B. So our x will be equal to omega square matrix B into X. Let us say this is equation 2. Now, this equation 2 in matrix form can be represented as x1, x2 up to let us say xn, okay, is equal to omega square into the B matrix having components B11, B12, let us say up to nth value B1n. Similarly, second row में हमारा आ जाएगा B21, B22 up to B2n. Let us say at the nth row we will have B1n, BN1, BN2 up to BNN, okay, multiply by x1, x2 up to xn. Okay. Let us say this is equation 3. Okay. The process of iteration, or you can say the process is then started by calculating a set of deflection for the right column, and then expanding the right hand side okay. This process is continued until the first mode repeats itself. The iteration process with the use of equation 3 converges to the lowest value of omega square, so that the fundamental mode of vibration is mode of vibration is obtained. Okay. So, to obtain the next higher modes, and the natural frequencies the orthogonality principle is applied. Okay, to obtain a modified matrix equation, okay, which does not contain, you can say, the lower modes. Okay. Now we will take an example so that it will be clear to all of you. Let us say we have an example. We have a system, multi-degree of freedom system like this. Let us say its stiffness is 3K, K, the masses are 4m, 2m, m, okay, and the displacements are, let us say, x1, x2, x3. Okay, this is the multi-degree of freedom system having 3 masses, 3 springs connected to them, okay, and overall they are on a rigid support like this. Okay. Now in the question, let us say it has been asked to find the fundamental natural frequency and corresponding mode shape for the system okay, using मैट्रिक्स इटरेशन मेथड. क्वेश्चन ये है, हमें इनका फंडामेंटल नेचुरल फ्रीक्वेंसी निकालना है और जो है कॉरस्पॉन्डिंग मोड शेप्स निकालना है यूजिंग द मैट्रिक्स इटरेशन मेथड. ओके, सो फर्स्ट व्हाट विल डू, we'll write down the differential equation of motion. Okay, the differential equation of motion equation of motion for the system will be 4m x1 double dot plus 3k x1 plus k x1 minus x2 equal to 0. Then we'll have 2m x2 double dot, okay, minus k x1 minus x2 plus k of x2 minus x3 is equal to 0. Then we'll have m x3 double dot, okay, minus k of x2 minus x3 is equal to 0. ये कहाँ से आया हम लोग का? जो पहला इक्वेशन है, it will be let's say 4m x1 double dot is equal to minus 3k x1. अब आप समझ सकते हैं, जिसका बेसिक नॉलेज होगा they can find out this equation. So I am not elaborating. Let's say this is our first set of equation. So if you further simplify this, you can write further simplifying the equation will have 4m x1 double dot plus 4k x1, okay, minus k x2 is equal to 0. Then 2m x2 double dot minus k x1 plus 2k x2 minus k x3 is equal to 0. Then m x3 double dot minus k of x2 plus k x3 is equal to 0. Let's say this is equation 2. So in matrix form, four m 0 0 0 2m 0 0 0 m then x1 double dot x2 double dot x3 double dot plus 4k minus k 0 minus k 2k minus k 0 minus k k, okay, into x1 x2 x3. Okay, so now we'll find out the flexibility matrix. A, which is basically the inverse of stiffness matrix, K matrix. Okay, so our flexibility matrix A will be 1 by 3k, 1 by 3k, 1 by 3k, then 4 by 3k, 4 by 3k, 4 by 3k and 7 by 3k. Okay, let's say this is equation 4. Now you can write, so the equation can be expressed as a m x double dot plus x equal to 0. Let's say this is equation 5. Okay. Now assuming a steady state solution, assuming a steady state solution, let's say x is equal to capital X sin omega t. So x dot will be omega into x into cos omega t. Okay. X double dot will be minus omega square x sin omega t. Let's say this is equation 6. Now substituting the values in equation 5, we have omega square one by 3k, 1 by 3k, 1 by 3k, here also 1 by 3k, then 4 by 3k, 4 by 3k, 1 by 3k, then 4 by 3k, 7 by 3k. This is our A matrix. Then our mass matrix will be 4m 0 0 0 2m 0, then 0 0 m, then x1 x2 x3. Okay, is equal to x1 x2 x3. Okay, now or we can say that x1 x2 x3 is equal to omega square m by 3k into 4 4 4 2 8 8 1 4 7 into x1 x2 x3. Okay, equation 7. So here we will start the iterative process now. Okay, now for the first iteration the first iteration, let x1 is equal to 1, x2 is equal to 2, x3 is equal to 3. So, we will have 1, 2, 3 is equal to omega square m by 3k into 4, 4, 4, 2, 8, 8, 1, 4, 7 into 1, 2, 3. Okay. Or you can say it is equal to omega square m by 3k into, if you multiply this, we will have 11, 32, 41. Or you can say omega square m by 3k into, taking out 11, the lowest value, we will have 1, then 2.9, 3.7. Okay. Now, coming to the second iteration, now we will take the values as x1 equal to 1, x2 is equal to this previous values we will choose, 1, 2.9, 3.7. So, x2 is 2.9, x3 as 3.7. So, our equation will be 1, 2.9, 3.7 is equal to omega square m by 3k 4, 4, 4, 2, 8, 8, 1, 4, 7, 1, 2.9, 3.7. Okay. So, we will have omega square m by 3k into 13.5 okay. So, omega square m by 3k into 13.5 will be 1, 3.1, 3.9. So, in the third iteration, we will take x1 as 1, x2 as 3.1, x3 as 3.9. Okay. Now, our equation will be 1, 3.1, 3.9 is equal to omega square m by 3k into 4, 4, 4, 2, 8, 2, 8, 8, 1, 4, 7 into 1, 3.1 is equal to omega square m by 3k into 14.1 will be 1, 3.15, 3.98. Now you can see here with the previous iteration that the values are not repeating itself. So, we will go on, okay, for the further iteration. So, in the fourth iteration, into 1 x2 3.15, x3 will be 3.98, 1 3.15, 3.98 is equal to omega square m by 3k into 4 4 4 2 8 8 1 4 7 into 1 3.15 3.98 is equal to omega square m by 3k into 14.28 to 1 3.16 4.0. So, here you can see the values of these deflections like 1 3.164 are quite repeating themselves as compared to the previous iteration 1 3.15 3.98. So, here we will stop the iteration process. Okay. So, you can write, it can be seen that the modes of third and fourth iterations are repetitive with sufficient accuracy. Okay. So, therefore, we will take omega square m by 3k into 14.281 to find out the fundamental frequency, the lowest mode. So, our omega will be 3 by 14.28 root over k by m. So, it will be 0.458 root over of k by m. Okay. And the mode shapes are, and the corresponding mode shapes are 1 3.16 and 4. So, this is the matrix iteration method way to solve a multi-degree of freedom system to find out the fundamental natural frequency and the corresponding mode shapes. So, in the subsequent classes we will continue with the orthogonality principle. Thank you.